Hi, in this lecture we are going to see or we're going to solve a problem. So I'm going to show how we perform a coalescence experiment. It, this type of experiments are performed both at lab scale and also at industrial scale. So it's essential to cover this topic as part of liquid extraction. So this is going to be slightly like an engineering calculations. We are going to scale up the process based on some experimental data that we can easily get from laboratory scale experiments. So what is this coalescence experiment is all about? It's the same whatever we talked so far. Liquid extraction is the same experiment, but we're just using the term. It's called coalescence experiment. I will tell why is that. So I'm going to read the problem, so or how we set up the experiment, so you will get some idea what we are talking about at the moment. So in coalescence experiments, we are performing this liquid extraction experiments in a 50-liter scale, and it is a cylindrical tank whose diameter is 0.40 meters. So just assume this is a liquid extraction experiment, and then we will come back to this word, what is this coalescence is about. I don't know how to spell coalescence or coalescence, whatever. And then the dispersion height has been measured at different times. I talked about this one in the lecture 1 or 2, I don't remember. And then we have a set of table values. So table value is here. We have something like time starting from 0th minute, 10, 20, 35, 50, 65, 80, 95, 110. And this is the height. I'll tell you what this height is about. So and then we performed a liquid experiment in a 50-liter scale cylindrical tank that has a diameter of 0.40 meter, and then we are going to repeat the same experiment in a slightly larger tank. So let's call this as an industrial scale tank. So and the working volume is going to be 1200 liter. So here it's 50 liter in this case, the lab scale experiment, and in the large scale experiment is 1200 liters. Again we are going to use a cylindrical tank, and this time we are going to maintain the diameter of 1.1 meters. Yeah, and then we need to calculate the time needed for separation or separating the dispersion into two different homogeneous phases. So I will explain you what does this mean by dispersion and different homogeneous phase. So quickly, this is our experimental data, and then I will show you what is this, how we perform the liquid extraction experiment. Obviously, just to follow the follow the green highlighter. So that's how we perform the experiment. We take our feed solution, which is in the bottom, that contains a lot of our solid particles. We add our solvent and then we agitate. So during agitation, what exactly happens is something like the one which is shown here in the second diagram. So we will disperse one of the liquid into the other, into the feed solution. Yeah, so that's how it will look like. If you put a stroboscopic camera, you can monitor even the movement of the dispersed phase. So you will have some liquid, and then one of the liquid will be dispersed, or it will become like a tiny droplets, and the solute molecules will move from these droplets to your other side of your liquid. So what we call, so if you take this type of sediment like a tank where we are performing this experiment, you see this one of our liquid is completely dispersed, and we call those phase as dispersed phase, and then there is another liquid which is carrying that dispersed phase. We call them as a continuous phase. So you have a continuous phase, and then you have a dispersed phase. So that's what you should know when you are going to perform this liquid experiment. So throughout, so far what we talked is like how we perform the liquid extraction. At the end you have two different phases, but we never talked what really happens. Yeah, like I never said how the tank will look like when you are mixing these two liquids. That one liquid is your solvent and the second liquid is your obviously your feed solution. We never talked about how it will look like. So let's put it like that. So I hope you all understand up to this point. I made a few more diagrams or something like here. So this is not gas. So if this is our tank, and just imagine we are just stirring using some impeller, and this is our one of the fluid is completely dispersed. So we have a continuous phase and we have a dispersed phase. And then once you stop your agitation, and then the system will start to settle. So what we are going to name at the moment is like, let's call this the whole tank as a dispersed phase, because we see this dispersed phase, one of the phase is completely dispersed into the other solution. So keep that in your mind. So once we allow the system to settle, this is what happens. So look at this diagram, the second diagram. Obviously we are going to get something in the top. Let's call that as extract. So let's call this is your solvent on the top, and the bottom is our raffinate. So what happened during the settling time is like the heavier phase likes to settle down in the bottom, something like I shown here. And so let's call that as a raffinate. And then the dispersed phase, they like to coalesce, they like to come together, and then they eventually they coalesce, and then they come into single phase on the top. So this will be your extract phase, and whatever which is in between them, this is still, we are going to call them as dispersed phase. Yeah. So this is how at the end of the experiment it's going to look like. We are going to have some extract phase, and we are going to get some raffinate phase, and there will be some thin line that's separating these two different phases. So normally this happens when your time reached something called as separation time. So when time is equal to separation time, we will clearly have two different phases, extract and raffinate side. So let's go back to a few more terminologies that we didn't cover while we are taking this lecture. So I will quickly explain it to you. So this is really easy one. Yeah. So I said to you what is a continuous phase and what's a dispersed phase. So the blue dots, they are dispersed phase, and the pink ones, they are continuous phase. Yeah, like everything is connected, there is no break. Whereas the dispersed phase, there is a boundary, and then some continuous phase is in between two dispersed tiny droplets. So I hope you all get this one. And what in the experiment, if you go back to the experiment, I gave you some table, time versus height. So this is something really important if you are going to design some tank like this. So this has nothing to do with your ternary diagram or anything. This is just we are going to calculate, or what's the time I need to separate the two different phases. So few more notations or some terminologies that you should know. So this is our tank where we are performing all this experiment, and then whatever the phase which is in the top, obviously it's going to be lighter phase, and whatever in the bottom, we can call them as a settling phase. And then the top of this settling phase, this border, we can call them as a sedimentation front. So this sedimentation front is going to increase once you stop your mixing, until it reaches some point. Whereas and the line which is at the boundary of your lighter phase, we can call them as a coalescing front. So your dispersed phase, they will coalesce together, and then they will eventually settle into separate phase, something like here. So coalesce is like you have two tiny droplets, they come together, and then they become one droplet, and it will combine together with another droplet and eventually become into clear phase on the top. So there is this front we call this as a coalescing front, and this one we call this one as a sedimentation front. So in the experiment what I gave you is the distance between the coalescing front and the sedimentation front. So when time t equal to 0, we will not have this coalescing front and sedimentation front. Yeah. So but once you, with respect to time, we will develop these two phases, lighter phase on the top and the settling phase in the bottom, and in between we will have this dispersed phase. So in between the coalescing front and sedimentation front, we will have this dispersed phase, and with respect to time, both will your dispersed phase, it's going to decrease with respect to time, and your sedimentation front, it's going to increase with respect to time. So at the end of the experiment, your lighter phase will come to, let's put some color. I'm going to use a highlighter just to follow the highlighter, blue highlighter. So eventually it will come to some point. So on the top you will have lighter phase, in the bottom you will have sedimentation front. So in the experiment what you have is, if you come back to this diagram, so here I just wrote it. For the moment let's assume we are measuring the height of the dispersed phase. That should be equal to, if you come back to this diagram, at time t equal to 0, that should be equal to the height of your liquid in the tank. Yeah? And with respect to time, they are going to settle and your dispersed phase is going to decrease. So if you manage to plot, say like you take a time on the x-axis and then you put the height between your dispersed phase and then your sedimentation front, or the distance that separates your dispersed phase, or sorry, your dispersion sorry, the height that separates your coalescing front and your sedimentation front. So that's what we have. Yeah? And then eventually this will come to some constant value, which means at this point, say follow this line. So at this point we call this as a separation time. So at this time there is no, how do you call it, there is no, you cannot observe a significant decrease in the dispersed phase, and you might have almost reached to a constant. So you would have a clear extract on the top and then you will have some raffinate on the bottom side. So you will have a lighter phase and there will be which lies on the top of your tank, and then the heavier phase which will settle in the bottom. Yeah? So that's the experiment. So this thing we didn't cover when we are talking about liquid extraction, but this is something you should know because we are going to scale up this process using some set of experimental data that we measured. So this is the experimental data that we have. So this is performed in a lab scale reactor. Anybody can go to a lab, take a 50-liter reactor and then perform this type of experiment. And at time t equal to 0, 40, that's the height of your dispersed phase, and then that's the height that separates your sedimentation front separates the sedimentation front and the coalescence front. So if you come back to this diagram, so this height, let's put some, follow the red highlighter. So this is the height we have. So this height is going to decrease with respect to time, and then eventually it will come to a constant. So this is your coalescing front, this is your sedimentation front. Or you can say this is your dispersed phase, which will eventually decrease with respect to time, and then this is the height of your sedimentation or settling phase. It will increase with respect to time. So this part which is decreasing with respect to time, this is nothing but this one, this height, the dispersion height. Yeah. So how to scale up this one? So I said to you, so if you come back here at 1/10 minute, the height is only 1.14 meters. So what does that state? What does that mean? So if you plot here, or maybe I already plotted here. Here I plotted time versus the height. Height that separates the coalescence front and then your settling front. You see, this is, you start at 40 and then eventually you come to 1.14. So what does that mean like? So there is a tiny gap in between those two different phases. There will be a small amount of dispersed phase. That's why you have something around 1.4 meter at this point. 1.4 meter. 1.4 meter, or sorry, 1.4 centimeter. So it's almost a negligible amount. So this is 1.4 centimeter. So if you allow, if you wait for extra time, so this is we achieve this level of separation when the time is 120 minutes. If you are going to wait for one more day, obviously this number is going to come to 0. So there will be a thin line. So you will have a clear extract and clear roughness. But it's a laborious process. It's waste of time, in fact. Yeah. So what we do is, like, normally we stop the experiment, we separate, we remove extract, and then we separate raffinate, you know, to collect our product from the extract side. So this is our experiment, and we achieved the separation in 1.4 centimeter. Sorry, we achieved this separation in 110 minutes precisely. So what I'm asking you is, like, if you're going to perform the same experiment, same liquid, same solute, same solvent, same temperature, and just assume we provided complete mixing, like the one, or at the same level of mixing like in your laboratory scale reactor. So what will be the separation time? You know, the separation time is not going to be 110 minutes. So that's the take home message you should out of this problem. Yeah. So this one we cannot give a separate lecture on this one. So what we are going to learn is, like, this height of dispersed phase, or the height of the tank, plays a big role on the separation time. So typically in industries, they like to separate these two different phases as quickly as possible, so that they can use the same tank to deal with different batches, which means they can improve their productivity. So that's the purpose. So what we're learning is, like, why the height plays, or what's the role of height on the separation time. So that's what we are going to learn through this experiment. So there are some people, they did a lot of experiments. They used a different combination of solvent and solute and different combination of feed solution, and then they did this type of experiment, and then they came up with an empirical equation, and their empirical equation is given by, is here. So this is not with one experiment. They performed with a wide range of experiment. They varied the dispersed phase. So this is the viscosity of dispersed phase, and rho c, this is the density of the continuous phase. So what they did is, like, they took a feed solution, they took some solvent with different viscosity and density, and then they performed a lot of experiment, and then they tried to correlate the separation time with the height of the height that separates your sedimentation front from the coalescence front. And then they found that the relationship follows a simple relation. So it's which is something like your time of separation is proportional to viscosity of your dispersed phase, and then density of your continuous phase, and then the density difference between these two phases, and then multiplied by height. And then if you observe here, So time of separation is proportional to height, but it's not linearly proportional. You have something to the raised to the power of 0.7. Yeah, so it's not a linear relation. So keep these things in your mind. So that's the relationship you need. So what I gave you in the problem is I didn't give you any information about the viscosity of the dispersed phase, and we don't have any information about the density of the continuous phase, and we also don't have any information about the density difference between these two different phases. But still we need to calculate the separation time if you're going to perform the same experiment in a large scale reactor. So this is really simple to perform. So what we need to do is like we need to take the ratio. We take the ratio. So I can show you quickly here. So time of separation in the large scale tank divided by time of separation in the smaller tank, that will be equal to the height in the larger tank and then the height that separates the coalescence and the sedimentation front in the smaller tank raised to the power of 0.7. And since the remaining all are constants, say like density and then also your viscosity of your dispersed phase, density of your continuous phase, and even their density difference, everything is a constant. So constant divided by constant, so both will get cancelled. So now we have a relationship between time of separation in a large scale reactor and in a smaller tank. So we can use this one in order to get your final answer. So how to get the final answer? For that you have to, so how to do this? So we need to calculate the H0 in the large tank and then H0 in the small tank. So H0 is nothing but your initial condition, which is here. This H0 we can calculate from the volume. So we know the volume of the dispersed phase. So I said to you we are to go back to your question. So 50 liter scale cylindrical 50 liter scale cylindrical tank, and the diameter is 0.40 meter. So from that we can get the volume. So volume of a cylindrical tank is V is equal to pi by 4 diameter of your tank raised to the power square multiplied by your H0. So we know the volume is 50 liter, so that's equal to 0.050 cubic meters, and diameter of tank is 0.40 meter. So once you substitute, we will get H0 value, which is 0.398, which is roughly 0.4 meters. And then you can do the same for the larger tank. Just use volume is equal to pi by 4 diameter of the tank raised to the power 2 and multiplied by H0, height of the tank. So we know the volume is 1200 liter, that's equal to 1.2 cubic meter, and then the diameter of the tank I already gave in the problem, which is 1.1 meter. So if you substitute both of these values, from there we can get the H0, which is the height of the dispersed phase. And then from this one we need to calculate the time that we need to separate in the larger tank, starting from a height of 1.26 meters. So all we need is to go back to this equation which I showed you here. So we know the time of separation in a small scale reactor is 110. So time of separation in a large scale reactor is just you multiplied this value, time separation in a large scale reactor, that should be equal to time of separation time in a smaller tank, H0 of a smaller tank raised to the power of 0.7. This is 1. I already did this where I solved this problem. 110 multiplied by 1.26, that's just now we calculated this one. That's the height of your dispersed phase when time t equal to 0 in the larger tank, and this is 0.4 height of the dispersed phase in a smaller tank, which is 0.4 meter. So we need 246 minutes. So you can see the time difference. In the smaller tank, the time we need is 110 10 minutes. In the larger tank, it's almost twice, 246 minutes. So that's the answer. You might expect this type of questions in the exam. Yeah, so you should know what type of equations you should use, and then you should try to solve. Yeah, you have to scale up the tank, and then you have to give me what's the separation time that we might expect. So this is an empirical relation, so nothing is accurate. So this is one of the many empirical expressions available that allows you to calculate the separation time in a larger tank, provided if you have the data already recorded, or if you know the separation time based on some experimental values that you performed using a lab scale reactor. So this is one problem in your something related to liquid extraction. I will solve two more problems, and then we finish this particular chapter on liquid extraction.